Materials innovation touches everyone's daily life. For example, smartphone technology would not exist without advanced materials like the Gorilla Glass on your phone, or transparent conductors and LEDs that create a touchscreen, the electrode materials that allow us to have safe, high-energy lithium-ion batteries, and semiconductors that make up the processing and memory chips that we have come to depend on daily life. The light bulb is a symbol of innovation. Thomas Edison didn't invent the incandescent light bulb, but he perfected it through materials innovation, trying hundreds of different materials for filaments before he found one that would be durable, bright, and relatively efficient. Edison also had to innovate in materials to do metal glass seals to maintain the vacuum inside the glass bulb while connecting the circuit. Practical electric light changed the world. Welcome to the IQT Podcast. On today's episode, we'll discuss the history of advanced materials, how they're developed today, and what the investing landscape looks like within this industry. I'm your host, Vishal Sandesara, and joining me today are Victoria Chernow and Steve Taub. Victoria is a technology architect on IQT's Field Technologies team. She has a PhD in material science from Caltech. She's worked as a fellow at ARPA-E before joining InQtel, and she looked at innovations in next-generation nuclear energy and engineered biology for energy and materials manufacturing, among other areas. Steve is a partner on our investments team. He's a reformed mechanical engineer, worked in government and industry, has 10 plus years of experience as a corporate venture capitalist before coming to InQtel in 2019, where he focuses on industrial technology, energy, advanced manufacturing, materials, aerospace, autonomous systems, among other things. Vicki and Steve, welcome to today's show. Thanks for being here. Glad to have you.
Thanks for having us.
Yeah, happy to be here.
So before we begin, let's set the stage with some definitions. I imagine a lot of our listeners, like myself, probably don't have too much of a concept or an understanding of what an advanced material even is. We certainly have an inclination that they're important, and they're probably pretty ubiquitous. But Vicki, can you define for us what an advanced material is?
Sure. So we like to quip that Madonna, being the science expert that she is, got it right. We are living in a material world, and the materials that we rely on, as you spoke to at the beginning, are advancing at a quite an exponential pace. And so the term advanced materials has been in circulation since about the 1950s. Explaining what an advanced material is, we can turn to this Bureau of Mines review from 1987, which basically stated that advanced materials are those that possess novel or unique properties or exhibit greater mechanical, thermal, electrical, optical, chemical properties relative to quote-unquote traditional materials. And so while the specifics really evolve over time of what it means to be advanced, the definition, at least let's say in my book, remains constant for what's an advanced material, and basically remembering that today's conventional materials were yesterday's advanced materials. Can also go into perhaps why we should care about advanced materials, but that could also be a separate, piece of conversation.
I like what you mentioned about conventional, yesterday's advanced materials becoming today's conventional materials. I think at some point in our conversation, we should certainly touch on the adoption curve and somehow, examples of interesting things that might have been, that we take for granted today that perhaps were once considered advanced. But before we get into that, let me ask you, Vicki, what is it that someone like me or someone who's listening should why should we care about advanced materials? How are they really impacting our lives or making a difference or making our lives, better in some ways?
Yeah, sure. So advanced materials provide a lot of opportunities, as you said, to make our lives better. They provide the opportunity to make things more energy efficient, to offer superior performance at lower cost, which is definitely important for a lot of our consumer goods. And kind of from this higher level, perhaps national security aspect, they also lessen our dependence on imports of strategic and critical materials or minerals. So kind of advancing what we can do with less, advancing what we can do with more ubiquitous or available materials is definitely a step in the right direction in some sense.
Yeah. Sounds like what you're saying is...
I might argue that, one way where maybe the definition of advanced materials has changed is that, there's a lot bigger focus today on sort of the environmental footprint of materials, which, in 1987, at least as far as I remember, it wasn't nearly as big a deal. And actually, I think, advanced materials are going to be a big factor in helping us, build a more sustainable economy, right? Whether that's, materials for solar panels to create renewable energy, or, materials to lightweight our cars and have longer range electric vehicle batteries, or, just a myriad of other things.
So it sounds like from what you're both telling me, there's certainly a lot of importance and significance to advanced materials and the impacts that they have to not only me, but certainly our future as a population, both strategically as a population of people in this country and also globally. Steve, touching on that, let's talk a little bit about development. Can you tell me, let's start with just where are these things invented or discovered, and who's doing the work in that regard?
Yeah, I mean, people are inventing advanced materials all over the place. I mean, lots of universities have material science programs and materials development labs. The government does a lot of work in this area, national laboratories, for example. A lot of big companies do this work as well. Whether they're in the industrial realm or the electronics or the chemicals, and even consumer products companies do advanced materials research. Even in things like healthcare, there's a lot of materials innovation going on. And then finally, which is where kind of IQT gets involved, there are startups who are working in the advanced materials realm.
Can you tell me a little bit about the process for new material innovation? How does the research process look? How does sort of the development process look? And how might it be either familiar or dissimilar from other more conventional disciplines?
Yeah. Well, look, I mean, I think there's sort of two ways that people approach this question, right? Some people find a new material, then try to figure out what to do with it. And other people have an application and they're looking for a material to make it work or make it better. Like graphene, people might have heard of, right? There's a great example of, some scientists, and I don't even know where, found this new form of carbon that had all sorts of great properties, and people are still trying to figure out what to do with it in a commercial sense. But at the same time, the people who make things like jet engines, have always been looking for new and better materials to be able to make the engines, more powerful, more fuel efficient, more durable, et cetera. So it kind of comes from both those directions. And, Vicki, I don't know if you have any thoughts on this. You've actually done this work. So.
Yeah. Well, I suppose I come from the university side of things, and a lot of experimentation, a lot of really hands-on work goes into it. I think kind of to another component of what you said, Steve, is frankly the timeline that it takes to develop some of these materials in these larger companies or even in startups. It's highly heuristic or experimental and can take years, if not decades, to kind of get where you want to go. So in some sense, one of the forefronts of the advanced material space will, in our estimation, be advancing the life cycle or the timelines in order to get to something that will really make a difference. So cutting down this time from decades to months, if it's possible.
Yeah. I want to just sort of build on that point about it taking time, because that is really definitely something I've seen. I mean, so I think of the example of like carbon fiber, which I think people these days know what carbon fiber is. People probably don't know that they were invented, like modern carbon fibers were invented in 1958.
Wow, I did not know that.
Yeah, by Union Carbide, actually, in Ohio. People realized early on that, they had some fantastic properties. They were really strong, they were really lightweight, they were also really expensive. In the late 60s, Rolls-Royce tried to commercialize them to make jet engine components. Didn't go so well. It actually bankrupted Rolls-Royce. So that was not a pretty story. But, at the same time, in the 70s, people figured out, hey, we can make sporting goods with this stuff. Fishing rods, golf clubs, skis, bicycles, tennis rackets. And that actually took off. I don't think that's what the Union Carbide guys had in mind when they invented this stuff. But around the same time, actually, you also had, in the 70s, you started to have, like fighter jets being built with carbon fiber composites. And then, 15 years behind them, roughly, you had the commercial jets starting to be built with carbon fiber, which, they had to sort of prove out the performance and drive down the cost to make that viable. So, here we are, literally, 60 years in from the invention of carbon fibers. And it's, we still haven't completely, we still think of them as advanced, and we still haven't completely, developed the market for them, right? I mean, I think the next frontier might be automobiles. We're already starting to see a little of that.
Yeah, it seems like the possibilities are endless. Today's jet engine, tomorrow's fishing rod. Earlier in our conversation, we talked about this concept of the time continuum. Yesterday's advanced materials being today's conventional materials. Do either of you have another? We talked about graphene. Do you have any other examples of things that are so pervasive in our life that maybe we've taken for granted that in fact started out perhaps not having an entire application dedicated to them at the onset, but in fact was an advanced material that is important to us today?
Well, I mean, if I can quote the movie The Graduate, plastics, right? I mean, if you go back to like the 1920s with the first, bakelite and phenolic resins, and now we've got, literally tens of thousands of plastics that are used in everything that we can think of, right?
That's right. There's actually also a giant island in the ocean that's made of plastic now, I hear.
Yeah, that
unfortunately.
Unfortunately.
That's a great example of how the development never stops. Right now, people are trying to figure out, well, how do we make plastics that are going to biodegrade so that we don't have this problem in the future?
Yeah, the evolution of an advanced material. It's a good thing to think about. Vicki, we've talked about the history. We've talked about definition. I think we have a good sense of sort of the foundational knowledge we need to have this next part of the conversation, which is let's dig into the types, just general broad-based categories of advanced materials. I know that you spent a lot of time thinking through and have a lot of experience with the different types. Could you first start by maybe just categorizing or binning sort of the big, broad types of advanced materials that are even important to consider?
Vishal, that is a great and daunting task because the potential landscape is just so incredibly vast. And on top of that, having these like consistent hard definitions or classifications is, difficult if not kind of impossible to produce. But for our purposes, we could potentially categorize them using sort of like a dual track approach. So one of those categories can live along what are the physical or chemical characteristics of this material, and namely something along the lines of, is it a metal? Is it a polymer or a plastic, as Steve mentioned? Is it a ceramic, like the material that your coffee cup is made out of? Or alternatively, the material that most of our high-temperature gas turbine blades are coated with. On the flip side, we can also categorize in terms of what is the application or the functionality that the material displays. And this in itself is also a really extensive list, and it can span from things like what are the surface properties of the materials, like can it prevent things like corrosion? Does it have electronic properties? Like, is it conductive? Is it insulating? Does it have magnetic properties? Does it have mechanical properties like higher strength, higher toughness, super lightweight? So, yeah, I'd say definitionally we can either think what is a thing literally made out of, or what is the application that it's used for, and then kind of span between those two sections in terms of what is the appropriate material for the particular application that we want? Because at the end of the day, there are things like plastics that have electronic properties, which kind of crazy to think about, but yeah, totally.
Well, I mean, it's almost a matrix, right? You have sort of, types of materials, ceramics and polymers and proteins and along one axis, and you've got applications along the other. And I mean, there's all kinds of surprising stuff. Like, Vicki and I have been chatting offline last few days about like people who are building satellites out of wood. So people come up with surprising combinations sometimes.
It really is. Steve, I know that you're going to lead us through part of the conversation around, where the investment activity is taking place. But before we jump into that, let's talk a little bit about demand. It's something that you and Vicki are bringing to attention is simply that, you've got this matrixed way of thinking about advanced materials by material or by function. Where is it that the demand is seen? What is it that, I imagine that a lot of the supply follows the demand in this scenario, especially given the sort of long time, development cycles and the costs associated with this. Where is it that you both have seen a lot of the demand come from on the function side, at least?
So you mean like what kind of functions are people looking for?
Yeah, what kinds of functions perhaps lend themselves really well to someone considering maybe I should look at the materials innovation scene to address this function, or instead of relying on things that are currently in the market, maybe I need to innovate, and the way I innovate is by doing materials innovation.
In some sense, it comes from everywhere, but I think there's a lot of demand for materials. There's a lot of demand still for materials with structural properties, right? Just we're always looking to make things stronger and lighter and more durable and things like that. There's a lot of demand for electromagnetic properties, I'd say, right? Electricity, magnetism. That's another pretty big area. What else? Vicki, you must have.
Yeah. I'd say that there are some like high level trends that kind of motivate the search for new advanced materials, and part of that is, as Steve sort of mentioned, the desire for consumers and companies to be more eco-conscious or sustainable in the materials that they're looking at. So definitely innovating around the need to mitigate climate change is a huge thing that's motivating the evolution of a lot of these materials, but also kind of looking more recently at our history, right? Managing the impacts of COVID-19 has also led to some interesting innovations along the lines of what materials are out there that are antiviral, and how do we develop those things into the products that we use. And this kind of, I'd say, goes very much beyond like the antibacterial sprays and Clorox wipes that we kind of traditionally think of. It's the application of copper nanoparticles into things. It's the application of new kind of protein structures into like material surfaces. So, and also I'd say like the big data machine learning trends that are ubiquitous in a lot of industries are also very much impacting the advanced materials landscape. So
this reminds me of a question I have for either of you. On the production side, do advanced materials tend to be certainly we're motivated by the idea that an advanced material in its application might be better for the environment, might be better, more efficient, might be greener. But what about on the production side? Is it safe to say or safe to assume that an advanced material is also safer on the environment or on a global scale on the production side, or do these tend to sort of vary in terms of how healthy it is for us to even develop these in the first place?
I mean, I guess I'd say it varies. But I guess the good news is that people are considering that as part of the decision making process now, right? It's something that people start to think about from the beginning rather than an afterthought of once I've already decided on a material, I have to figure out how to make it without polluting the world. One other thing I think we're seeing as a demand driver is national security. The U.S. is, we're a big country. We have lots of resources, but we import an awful lot of our raw materials. All kinds of minerals, steel, all sorts of rare earths, so there's a lot of thinking about, can we come up with, new ways of extracting these materials from resources that we've got in abundance here? Can we find new ways of recycling the materials that we've already got here rather than putting them in landfills, or if you want to think about even, mining landfills? Or can we come up with alternatives, right? There's some really smart people out there trying to come up with high performance magnets that don't use rare earths, which almost all of which are processed in China, for example, or battery chemistries that don't need lithium, because we import most of our lithium in this country too. So there's a lot of innovation that's being driven by national security considerations.
Interesting. Vicki, did you have a point you wanted to add?
Yeah, I just wanted to kind of quickly plug the fact that it's sort of striking how many different industrial verticals, let's just say, rely on petrochemical byproducts out there. Obviously, you think about like the gas that's going into my vehicle or into like jet planes. That's obviously a petrochemical product, but a lot of that also goes into obviously the plastics that we use, as well as even more downstream kind of things like the pharmaceutical industry. So I think another kind of, again, to sort of harp on this point of sustainability and thinking about climate, it's also moving away from this petrochemical feedstock as the source for the materials that we're going to be using in the future. And it's a really hard challenge because we got very good at using every type of molecule that, comes from the oil that we get from the ground. So it's going to be quite challenging to figure out exactly how to replace everything that's in that value chain. But we're working on it. So
it's great to hear. Steve, I know that you've talked to almost 30 venture capitalists, including financial VCs and corporate VCs. In those conversations and what you've learned, who's investing in advanced materials and what are they looking for?
Yeah, that's a great question. Yeah, so we kind of did a survey of people that we knew were actively investing in this field. Both financial venture firms as well as corporate VCs, and what we found is, I mean, first of all, yeah, they are investing, and the activity is growing pretty quickly, actually. So, from 2018 to 2019, it more than doubled. So, over $1 billion a year is going into startup companies that are focused on materials innovation, in terms of what they look for, it's actually kind of interesting. Obviously, all VC investors look for certain things, right? Strong management teams, large markets, valuable innovations, things like that. But material investors, they have some particular lessons that they've learned over time about where they find the best return opportunities. So, they tend to like to invest in companies that are developing sort of specialty materials instead of commodities. Because specialty materials tend to be high value and high margin, and you usually don't need to invest a huge amount of capital in order to produce them at scale to make a big company. They also tend to like companies that are not so much focused on a material itself, but on an application for an advanced material. Most of the value that comes from advanced materials is not from making the stuff; it's from what you can do with the stuff. And that's a lesson that I think venture capital investors have learned over time. And then the other thing that we saw, which was maybe not surprising, and if you think back to my example about carbon fibers, right? It took a long time to figure out what the market for that was, and to really start to see that market take off. That's common across materials innovations, right? So where people come up with a new material and they try all sorts of different markets, and hopefully one of them eventually takes off. So the investors tend to like to wait until they see that inflection point, has arrived or is about to arrive, before they really kind of jump in with both feet and start funding companies heavily to scale up.
And when it comes to industries that might be the most active in the advanced materials arena, I know you've unearthed that healthcare, energy, advanced manufacturing like 3D printing, and bioproducts are sort of at the top of the list. Is there anything you can say about what do these industries have in common that lend themselves so well to this level of activity when it comes to this space?
Yeah, that's a good question. I think one is just these are all industries that invest a lot in innovation in general, and a lot of innovation ultimately is materials innovation. So I guess it's not surprising that these are sectors where people are really trying to develop and commercialize advanced materials to meet their needs, and they tend to be on kind of the cutting edge of performance, they're always looking to sort of push the envelope of what they can do.
Interesting. And as we look across, sort of leaving industry, let's look at sort of competition in the space, global competition in the space. Are there any actors that come to mind as sort of being equally or better positioned in this space?
Mm-hmm. Yeah, historically, the U.S. and Europe have always been very active in the materials world. Actually, a lot of advanced materials work is done in Japan and Korea. And China has really become a big player. China's a big player just in sort of the general materials value chain of producing, silicon for microchips and electrode materials for batteries and rare earth magnets I mentioned earlier, even just steel and plastics and petrochemicals. And they're really investing really heavily. A couple of years ago, they established a $21 billion, government fund focused on manufacturing. And they're just producing technical research at an accelerating rate. They're publishing twice as many papers as in material science as American researchers are these days. So I think China is probably the one to watch.
Interesting. That's great. Thanks, Steve. Let's shift gears and talk about the future of advanced materials. And before we start doing that, I just want to put a shameless plug out to those who are listening to check out the blog post that has been written about advanced materials. You can find it at iqt.org/blog. We'll have the link up in the show notes. You can find a lot of this information as well as other enriching information about this topic in that blog post, including a nod to what I think we should talk about next, which is sort of the future and the hype cycle associated with advanced materials. So, Vicki, open question to you, perhaps. What crystal ball in your hand? You're looking into it. You're telling us all, where are we headed when it comes to advanced materials? And Steve, feel free to chime in after.
Yeah. Well, as Steve alluded to, there is a ton of innovation that's happening in a lot of areas around materials development, but yeah, I guess in my estimation, two kind of areas to watch would be biofabricated materials, and then also was kind of mentioned before, the application of artificial intelligence and machine learning to the materials discovery and optimization space, which I guess more colloquially we call materials informatics. So those are two big areas where I see a lot of exciting kind of work happening, and also happy to kind of dive into some of the examples around that. But Steve, if you...
I'd throw in a third one, which is metamaterials. Yeah. So metamaterials are kind of materials that derive properties from their structure, not their chemistry. So like, a natural example is butterfly wings, right, which get their color from the structure of the butterfly wing, not from any kind of chemicals in them. But textiles are metamaterials, right? And there's lots of interesting examples where people are doing things like, structural lattices, for example, or using diffraction gratings to make optics, which is kind of a metamaterial. So it's an area where I think we see a lot of interesting innovations going on.
Interesting. Vicki, why don't you dig into a couple of the, you talked about biofabrication and biomaterials, you talked about materials informatics. Why don't we dig into that a little bit?
Yeah, for sure. So, by biofabricated materials, I mean kind of the next generation of biologically produced materials. So in some sense, the going beyond the traditional biomaterial. And so a lot of these are going to be produced using some sort of engineered microbes, using them as little microscopic factories to produce this thing. So a lot of innovations in synthetic biology, for example, go into this. And the really interesting thing is you can produce a lot of custom or specialty chemicals that you can't produce by synthetic or regular means. And you can also make these things using, let's say, non-traditional feedstock. So moving away from this petroleum-based feedstock for making kind of the traditional materials that we have today. And so these are kind of popping up in a lot of different industries. So we have things like alternative structural materials that are made out of bioconcrete. There are mushroom-based bricks and insulation. There's really interesting engineered wood products, which, as Steve mentioned, I totally love. Anything wood-based, I think that's a material of the future. And also some really interesting things that are made using fermentation. Again, whether that's, say, mycelium or these mushroom-based leather products or spider silks. And from kind of this interest level, this is especially cool because we now are looking at more of this domestic supply of materials, which improves supply chain logistics. Again, something that we saw kind of fracture during the COVID-19 experience. But additionally, a lot of these materials can display superior performance than kind of their traditional or petroleum-based kind of counterparts. And they can also exhibit unique or desirable functionalities, whether that's flame resistance or dissolvability. And the other cool piece is that biofabrication oftentimes leverages a lot of the informatics or AI processes that are becoming more and more ubiquitous. And sort of to that point, materials informatics is now this tool that we can use that applies data science and AI methods to better understand the use, selection, development, and discovery of materials. And so this is a tool that we can now use to identify exactly what material class will give us a particular property that we're looking for, or on the flip side, allow us to discover some kind of unknown property of a certain material class. Again, thinking about plastics that have electronic properties, just as an example. And so it's still kind of a nascent field, but there are, certainly plenty of large companies that are looking at applying this sort of technology to really accelerate their development cycles, which again can often take decades. So yeah, in my book, materials informatics, another really interesting thing to look forward to in the advanced materials space.
Steve, anything to add?
No, I think Vicki really covered it there. Materials informatics is really an interesting field, and it's enabled by the huge increases in computing power and data storage, and the availability of just massive amounts of data. So it's something you really couldn't do 5 or 10 years ago,
right?
Unless you were like in the lab.
Let me ask you, as we're discussing this, a personal interest of mine comes to mind. I'm generally really interested in just food science and food chemistry, and I'm reminded of a lot of my favorite foods that I've been consuming over the last few years. A lot of them happen to be made from these companies that have found a way to imitate or emulate animal protein, but by being completely plant-based. Can either of you comment on? Am I keying in on something there? Is that an example of how materials science and innovation, research and development might be playing into my stomach, for example?
Yeah, absolutely. So I think biofabrication absolutely applies to this food and beverage space. There are plenty of companies out there that are thinking about how do we make protein independent of the cow, either for meat or for dairy. There are companies out there that are producing dairy alternatives that still resemble cow-based milk. It's kind of funny that we even have to call it that because there are now so many of these alternative dairy products out there.
Yeah, no, absolutely. I mean, I think just being able to replicate the taste and the texture of these animal products without having an animal is a huge challenge, and I think it's basically a materials problem.
Yeah, that's what it sounds like. I just remember every time I go to a cafe or a coffee, I always want to ask the question, how do you milk an almond? And it turns out that question might become more ubiquitous than ever, thanks to material science. Vicki, Steve, we're almost at time. I want to thank you both for your time, your information, and the conversation today. I certainly found it very informative, and I hope our listeners will as well. Is there anything else you'd like to say as parting words to our audience?
Materials are everywhere, and I think that it's high time perhaps that people become a little more cognizant of how ubiquitous they are, how they affect your life, whether it's that phone that's in your hand or the burger that you're about to put into your body. Absolutely, a lot of innovation happening on a lot of different fronts. So it's just a very interesting space to be exploring.
Yeah, for sure. I mean, you said it well. I have nothing to add.
In case you'd like to learn more, please find our blog, iqt.org/blog, and scroll to the Advanced Materials post to learn about this conversation, and also learn more about advanced materials in general. I'd like to again thank our two guests today, Steve and Vicki. Thank you so much. We look forward to talking to you again. To our listeners, thanks for listening. We hope to catch you on another episode of the IQT Podcast. Thanks and goodbye.